They sort of disappeared. Yeah. Okay, people, I propose that we get started.
I think you have.
Some people short. Anyway. People, I'm sure you've seen the exam grades. There's some points that I would like to make about the exam. There are a couple of things that I think it's good to discuss a little bit with everybody. Some typical answers that I saw that I think, well, you might need a little bit of update on. But I think I would like to do this during the 2 tutorials because we have much more time for one-on-one interaction. Now, one-on-one does not mean I wrote down this. Can I get a point for that as well? We also will have one of those sessions. Yes, you will still get an invitation where you can look at your personal exams. But I would like to reserve a little bit of time from the tutorials to say a couple of generic things that I think, well, next time make sure that you don't write down something like this because of that reason and such. Yes, some generic tips for everybody that I picked up while grading. Leaves us for today. Do you remember from our starting lecture a month and a half ago or so, a little bit more, what the goal is for today? Right, we started in lecture 1 by saying this is what we're going to do throughout the next couple of weeks. Do you remember what it was?
Interaction.
Interaction, good. I hear a word. That was also your word, I'm very sure. Yes, we are going to look at interaction. Last week we started with indeed what I like to call the more active part of special relativity, where you're not just looking how things are happening, but you're actively participating in it. But it sort of led you astray because it gave you the mathematical formalism to do these calculations. That was Lagrangian formalism. But then it turned out during the tutorials that the Lagrangian that we've been using was still one where things were moving with a constant velocity. Which is another way of saying you're still not interacting, right? I mean, if there's one characteristic of things that you're interacting with, is that they don't go with constant velocity anymore. So I gave you the formalism to do interactions, interactive special relativity, but we haven't quite done it yet. But this was the groundwork that we did last week. So we're going to continue with that this week. We are going to talk about how does nature look? How do the rules of physics look at the moment that you have special relativity, so Minkowski space-time, including all the weird stuff between space and time that happens there. But you yourself are actively participating. You are pushing and pulling against particles and masses and these sorts of things. Yes, that's the plan for today. So let's get started. Now, by the end of today, this lecture, you will not only know how to do that, you will also know the general rules for special relativity. And that means, well, really my job then by that time is done. There's hardly anything else to tell you. I've told you how things look from one frame to another, Lorentz transforms, why they look that way. And by the end of the day, you will also know, if you start interacting, how that will look and how that works. And the only thing you have to do is pick the right Lagrangian, depending on your physics, and work your way from there. So I think that really nicely caps off our forays into special relativity. But first, let's get started with a small summary of last week's formalism. This is by now is one of your best friends, I guess, yes? It's the Lagrangian. Where does Lagrangian come from? Well, depending on your field of physics, it comes from the same mysterious place where you got your forces from in Newtonian physics, either experiment or because you had some deep theoretical insight where it comes from. But once you have a Lagrangian, you're all done, yeah? We're not going to repeat all the steps, but one of the things you can do once you are given a Lagrangian, this piece of physics corresponds to this Lagrangian, then you know exactly how nature will behave. Nature will behave to make this thing as small as possible, which itself is mathematically the same as solving this equation, the Euler-Lagrange equation. So if somebody gives you a Lagrangian, you know how nature will behave. Just stick your Lagrangian into here, solve the equation, and you know how nature will behave. One other thing, again, I'll just summary at this point, but one other thing that Lagrangians will tell you is the energy. once somebody gives you a Lagrangian, you immediately know what the energy is of that system. It's this thing. And if you want, you also know immediately what the momentum is. That's this thing. And you also even know if they are conserved or not. So from the tutorial last week, when is this guy conserved?
When it's both position and velocity dependent.
What is?
The Lagrangian.
Correct. If, so this is conserved number. If L is Lx and Lv. So that really is almost all Lagrangians you can ever think of. So that's nice. And about this one? This is also conserved, but only under a particular condition that we also did during the tutorials last week.
If it doesn't explicitly depend on position.
What doesn't?
Lagrangian.
The Lagrangian, yes. If L does not depend on position. Yes? So we proved that last week. So that's very nice. Not only if I give you a Lagrangian, you know how nature will behave. That's all the left side here. You will also know what the energy and the momentum are of the system. And even if you have no idea what physics the Lagrangian describes, just by its mathematical shape, you can immediately tell this will be a system with a conserved energy, and the momentum in this system will also be conserved. Now, isn't that beautiful? I mean, I say this with no sarcasm whatsoever. Isn't that beautiful? I mean, how great that is. Also, if you have the Lagrangian, we haven't fully worked with it, but I have noticed it to you in both the tutorials, Newton's theorem. Now, depending on what you're going to do later in your physics education, you might or might not find this equation quite often. I always use Jacco and his particle physics course because in particle physics they use this all the time. Right? I know that some people in this group are doing Jacco's particle physics course. He talks about conservation of lepton number, for instance. Right? That's a number, that's the thing that he constantly uses. Or the conservation of charge and all these things. They're all the direct result of the Lagrangian and Newton's theorem. So this is why I made such a point in the tutorials last week of specifying that this theorem exists, even if we're not using it explicitly in this course. It is very important that at least you know of this. So I took the freedom to put on Aleum a nice little Wikipedia article on Noether herself, the scientist, including the work that she did and where she did it. Also the terrible story, sociologically speaking, of her not being paid for getting all these beautiful results. But here we are. All right, all of this is just a summary of last week. And there were two Lagrangians that we actually specifically looked at. There's many more that you can look up in the books if you want. You literally have books, this has tables of Lagrangians for all kinds of physics and biology and chemistry, but there were two that we explicitly looked at. One of them still, I am only summarizing last week. One of them was the Lagrangian corresponding to Newtonian mechanics. It was 1/2 mv squared minus whatever potential energy is in the system. And there was the other guy for special relativity.
Negative mc squared over gamma.
Exactly, negative mc squared over gamma. And I think one of the most important points that I wanted to convey to you in the tutorial of last week was that this guy isn't a happy guess. We don't take this Lagrangian to be the Lagrangian because it gives us something that we already know should be true, right? In principle, if you give me a piece of physics and I already know from other sources what the energy should be in that piece of physics or how nature should behave, so I already know what the outcome of this equation should be, and I already know of that piece of physics what this equation should give me, then I can sort of reverse engineer towards my, well, this then must have been the Lagrangian, yes? That wouldn't be very useful, because the best thing I can end up with is a Lagrangian that gives me the stuff that I already do. So it's very important that you understand of the tutorials last week that this Lagrangian doesn't come to us because we know what the answer should have been. We got it from a deeper principle, and can I ask you, do you remember what that deeper principle is? Why does the Lagrangian have this particular form? For what reason?
It has to be invariant because the integral over Lagrangian has to be the smallest number for everyone.
Yes.
Not just for some observers. And if it wasn't invariant, that would be a problem because you would have different.
Yeah, but this is not invariant. This Lagrangian. It's V dependent, and V is not invariant. So you started by saying, well, L has to be invariant.
Yeah, but this. I mean, this gamma can go with this dt to
Yes.
give d tau.
So this gamma goes with this dt, and together they make a d tau via Lorentz transforms or so, yeah?
Yeah.
Or time dilation.
The action has to be
The
invariant.
action has to be invariant, and I know this is what you meant.
But I said the integral over
Oh,
Lagrange.
I'm so sorry. Then you're completely right. Yes, okay. Yes, this guy is not invariant, right? It's the integral over it. The action that is invariant. And yes, the reasoning that we applied was that special relativity says that the rules of physics, whatever they are, should be the same in all inertial systems. Not just the speed of light should be the same number, all the rules of physics should be the same number. But this is what gives you the rules of physics, the smallest value of s. So if you want the smallest value of s to be true in all coordinate systems, all inertial systems, then obviously s cannot be coordinate system dependent, because then you might have that this guy's smallest s and this guy's smallest s for the same system are a different number. They would get to different rules of physics. So we had no choice but to construct a Lagrangian that put into this action gives an invariant smallest number. Yes? So even if you had never heard of special relativity at all, well, suppose that you never knew how the Lagrangian looked. Just by knowing that the action should be invariant, because you want the rules of physics to be the same in all inertial systems, that was enough to get you to this. Okay. So that's beautiful. Then we plugged both of these into all these equations. This guy gave us that the energy of this system is this. This guy gave us gamma mc squared. Yes. That's very nice, because we also derived this formula using what I call the quick and dirty way, directly from the Minkowski line element. But it's nice to see that the Lagrangian mechanics gives you the same answer. It should. But we also found the rules of physics in those two systems. Do you remember what the rule of physics is that nature follows under this Lagrangian? So you get this Lagrangian, stick it in here, you end up with a new equation. I know that we did that.
You mean to find x and y? And
Well, yeah, ultimately, of course, what you want is how x and v behave as a function of time, yes? I mean,
yeah.
that's what that rule will tell you. Now,
It's the integral of.
yeah, no, I know. The actual expression for x and v are long expressions of integrations and everything, but it turns out
We get 0.
that was this. Right? If you stick this Lagrangian into this rule, you get that the derivative of the velocity times the mass equals minus the spatial derivative of the potential energy. And the spatial derivative of the potential energy is by definition the force. So you just get Newton's second law. Which is nice. I mean, it says that this Lagrangian says that nature behaves according to Newton's second law. So that's good. How about this one? If you take this Lagrangian and stick it in here. So this Lagrangian, do it over here. How does this piece of nature behave?
Relativistically, so I would assume.
Yes, relativistically, agreed.
I don't know what answer you expect.
I mean, we established that we have a constant velocity. So
That's enough. We want to know how things move. Yes. When I say how does nature behave, maybe I should have phrased it differently. How do things move under this Lagrangian? How does this mass move? And then we indeed found that this Lagrangian tells you that whatever the mass is doing is moving with a constant velocity. Yes. Now, for the people who might not remember this from the tutorial a couple of days ago, this is an easy exercise. Stick this guy into here, work it out, you get v is constant. Now, and this brings us where we're really going to start today, namely v is constant, is another way of saying that you're still not interacting with it, right? I mean, it just says Newton's first law, and Newton's first law tells you that if you leave things alone, then they go with constant velocity. So therefore, because things here are going with constant velocity, it means we're still leaving it alone. So we have a Lagrangian, but we're really not interacting yet. Interacting means touch the thing, put forces in. So what we're going to do now is we're going to take this Lagrangian and extend it. We're going to make sure that it does describe something in which we are actively interacting with the system. The question is how to do it. Lagrangians are not listed in a book. Well, they are, but this is not how you should look at Lagrangians. They come from deeper principles. So the big question now is, how are we going to put in the possibility of things moving, accelerating? How are we going to do that? What are we going to do to the Lagrangian in blue over there, such that it now will also describe accelerating particles?
I mean, we need some function of x, because so momentum is not conserved.
I'm very happy with that. Yes. You're using this rule.
Yeah.
You say, well, p is constant, means with constant m, that v must be constant. So this conclusion really is this conclusion. So apparently we have been taking a Lagrangian that does not depend on x. That's true, because there's no x dependence. So it's at least consistent with this rule. So, but you're right. That means if we want to make this non-conserved, momentum is changing. That means we have to add something to this Lagrangian that is x dependent. Maybe also v dependent, but certainly x dependent. So that's good. I mean, that's a nice mathematical conclusion. What is missing from this Lagrangian in order to get an acceleration, and non-constant p means what is missing is an x-dependent part. Any more suggestions? It's good. I mean, it's a clue, but we're not there yet. Yes?
Maybe take the v in gamma and make it dx over dt, and then somehow...
Oh no, but the dx over dt is just another way of writing v.
Yeah, I don't know.
Yes. No, you're right. I mean, you might argue, well, a v isn't a v just like an x? Well, there's a time derivative,
But it's more implicit.
it's implicit. It's the difference between an implicit variable and an explicit variable, and ultimately it has to do with these being curly d's as opposed to straight d's. And I'm sure Ronald in his multivariable calculus has told you more about this. I'm just guessing. I wasn't there when he gave the course. But there is a difference between a curly D and a straight D. Curly D means only look at the things where the V's and the X's are explicitly mentioned, and don't try to sneak your way through X's that are hidden within other things. Okay? If you want to also have the X's and V's that are hidden in other things, then you use the straight D's. So there really is a difference, not just in notation, but in meaning between a straight D and a curly D. And the Euler-Lagrange equation really has curly D's over there. So you cannot make this V that is in here sort of look like an X, because these curly D's will not care about your hidden V's or your hidden X's. So any other suggestions?
We need to add some kind of interaction, because velocity should probably trying to take this.
So what I'm hearing is, so we have this guy, and what I'm hearing is now we should add something, and what we add to it should be x dependent. Why adding? Why not multiplying, for instance? Or change this altogether?
Multiplying doesn't change the outcome of your action. Or
Not with a constant, but with an x dependent thing, though. I mean, that is a thing. You could say, well, we're going to multiply it with something x-dependent. You could also say, I'm going to add something that is x-dependent. In both cases, we get the suggestion that something accelerating will enter your theory at this point. Pluses or multiplications?
Like if you take it as, like if you take inspiration from the other Lagrangian that we have, like
Yes.
a sort of plus, because then you'd have like two parts. One with speed,
Oh.
one with position.
No, I quite like that argument. Yeah. So here's the argument, I think, if I'm doing you justice here, yes? That as well, in Newtonian physics, you have a v-dependent part, plus or minus, but not multiplied, with a v-dependent part. So here's the v-dependent part, here's the x-dependent part. And special relativity is sort of like Newtonian relativity, but with a little extra, right? And maybe the little extra is already in the gamma here. Because of relativity, that gives you gammas, something like that. And maybe if we get inspiration, that I think that's even how you put it, if we get our inspiration from Newtonian physics, well, here it's sort of like a plus or a minus, so might as well try it here as well. Let's go with the plus. Well, that sounds good actually. It's not conclusive per se,
Then you can try it out.
but we can certainly try it out. Yes. No, all joking aside, but this is
Great
how
Sunday
people get
afternoon.
their Lagrangians. I mean, they look at things and say, well, it should be something like this-ish, so it should be something like that, blah blah blah. I'm going to take this argument, but I'm going to make it slightly stronger. Yes. So I like the idea of, well, let's take our inspiration from the Newtonian Lagrangian. Actually, I like that idea quite a lot. Yes, I wasn't planning on going there, but you know, now you give me this little bridge, this starting point. I'm going to use this starting point. I think it's a good idea. Let's take the Newtonian. Let's try to get our bearings from the Newtonian Lagrangian. Yes. Do you remember how you get from relativistic physics to Newtonian physics? There's one simple step that you have to take, and it always works out.
You make the velocity very small.
That's correct.
Or you choose C to be infinite.
Or we choose C to be infinite. That has to do with the personal discussion that she and I were having yesterday. So forgive me for not taking that step, but you and I know what we're talking about. It's not like I secretly give her information or something like that, but it just happened to come up yesterday. Yeah, let's take let's make V very small. Yes, this is relativistic. Let's put this here. This is relativistic Lagrangian, and we know that the difference between relativity and Newtonian physics is that, well, if V is very small, it should look like something Newtonian. So let's actually do that. Let's go here. Because I really like this suggestion. Again, I was going in a different way here, but I think this is going to work out. So I just wrote down 1 over gamma, right? Gives you this square root. And because we know that relativity at low velocity should give you back Newtonian physics, well, let's take Lagrangian and make it Newtonian physics. How do we do that? Make V very small. Small compared to C. And yes, going back to Elisa, that's equivalent to saying make C infinite, yes. It's about this ratio being very small. Okay. Do you remember how to approximate something like this? We've done it in some of the epsilon exercises.
Would be 1 plus 2 V over C.
1 minus a half?
I hear two options, 1 minus 1/2.
Don't you bring the exponent in front of the number that you...
I agree, but what is the exponent?
Oh, yeah,
Minus a
because...
half.
yeah.
Or well, a half.
It's 1/2. It's not
Uh-huh.
minus 1/2, it's 1/2, yes.
Uh-huh.
So there's no physics going on here. I'm only using what we call a first order Taylor series of this expression, which is always true as long as nx is much smaller than 1. That comes from first year calculus, Taylor series. All right,
Okay.
so we should now be in Newtonian physics, agreed? We've made this step. We said the velocity is much smaller than c, so in other words, if you would call this your x, that is a very small number. V is smaller than c, then v over c squared is certainly going to be smaller than 1. So this holds, so this holds, so this part should now be the Newtonian Lagrangian. It should look like, where is it, this guy. Now let's see what we have. Let's go with these two first. MC squared goes with this, c squared drops out, I get, now look at that. Isn't that nice? But we're not there yet. We have something else. Now I already know something. Whatever comes out next must be minus the potential energy, yes? So let's see what that is.
Well, But before we argued that that's also in there, we just don't write it.
What I are, well, let me get back to that. I mean, I understand. Let me first make this argument, and then let me go back to your question. So, if I forget about the plus fx for a moment, yes? This, in direct comparison to this, apparently mc squared is the potential energy due to a mass that's moving through Newtonian space, Newtonian physics. Now, this is not new. We already concluded this last week in a different way, because we said that if you take even when we were not when we were still doing the quick and dirty way, no Lagrangians whatsoever, we had already concluded that the energy of a system was 1/2 mv squared plus mc squared, and that the mc squared apparently is some amount of potential energy that is fixed to your mass. So this is not a new conclusion. We just see it in a different way, because we have 1/2 mv squared, exactly this. Whatever you subtract from it then must necessarily be the potential energy. Apparently that is mc squared in our original Lagrangian. So what we get is mc squared apparently really is the potential energy of a particle or a mass in relativity. So we have a new conclusion, or an old conclusion but derived in a new way. Potential energy of a mass, even if you leave it alone, is mc squared. I think this is your question a second ago. Didn't we argue that this hardly had any meaning?
Well,
it doesn't, because at the moment that you stick this Lagrangian, including the mc squared, into the Euler-Lagrange equation, Euler-Lagrange equation will cancel any constant that you add to your Lagrangian, yes? So as long as this is constant, then that means as far as the resulting physics is concerned, the rules of physics that come out of Euler-Lagrange, they will not change because you've added mc squared or subtracted mc squared. So this guy pops up as a necessary result of our Lagrangian, but in the rules of physics you will never see the mc squared actually coming out. Okay, so that means it's completely in agreement with Newtonian physics, where you never had to worry about the mc squared. So that's fine. All right. But now we have our suggestion of adding a plus fx. Because even with this guy, we still don't have acceleration because it's not x-dependent, and we were looking for something that is x-dependent, right? Now can somebody tell me, if we are now in Newtonian physics, but we want some f as a function of x added to it, what should that f of a function x be? All the ingredients are on the board. You just have to connect the dots. Right? So one more time. We argued that this guy, up on this point, cannot describe acceleration because of this rule here. We have a conserved momentum, which is another way of saying that the particle will fly with constant velocity, which is another way of saying it will not interact with anything. So we argued, or we were hoping, that maybe if you add a x-dependent part to it, then necessarily you will have something that will contain accelerations. And then we were taking the cue that maybe if we take our suggestion, including the plus fx, and then make it Newtonian, maybe then we end up with a situation where you can read off what fx should have been. So from this, please.
Wouldn't it be the relativistic force? The one with gamma cubed somewhere?
No. First of all, it's not a force because it has to be of the unit of an energy at the very least. It's an addition to a Lagrangian, so that means there's an energy in there. I see another suggestion.
Like the work?
Yes. No, I have no idea whether she's going to say the right thing or not, but.
Like the work? Like that on the system?
A work?
The work.
That's the work. Yes.
Yeah.
Now, if I it's fine. At the moment that I apply work to something, yes, work means you pushing and pulling against a mass over a particular distance. Then what happens is I raise the energy of that mass. Right? Work is another way of saying adding energy to another system by me pushing and pulling against it. Now we have a name for this energy that I give to a system by applying work to it.
Potential.
That's literally what we call potential energy. So could this be potential energy? In fact, shouldn't it be? Look, everything that you subtract in Newtonian physics from this part is by definition potential energy, isn't it? Now we already had some potential energy.
As a function of mass.
As a function of mass, fine. But if I literally just compare this expression for the Lagrangian as it should hold in Newtonian physics to the one that actually holds in Newtonian physics, then that part is that part, and then necessarily everything that I subtract from it, this must be potential energy. Again, the Lagrangian already gave us mc squared as part of the potential energy, but that was a part of the potential energy that didn't have any lasting results on how the motions happened, yes? But this guy does. So from this Q going to Newtonian physics and then just comparing this Lagrangian to what it should be, namely this Lagrangian, I can just read off whatever this F is, has to be a potential energy. Good. That means we have a beautiful conclusion now. So I'm now going to drop that I am in the Newtonian approximation. I've identified my F as a potential energy. Then this must be the choice. This must be it. So I very much like that Q. By comparison to Newtonian physics, I could just read off that whatever I add to this thing should have given me this. I'm sure at this point somebody would either raise a point or ask a question. Otherwise, I'm going to.
I don't know how you went from this to this.
Can somebody fill her in?
The last thing we wrote, the half mv squared minus mc squared plus fx squared.
Yeah, so mc.
That's the Newtonian approximation, which
Uh-huh.
has to be equal to what we know is true for the Newtonian, which is a half mv squared minus potential energy. So
Yeah.
that mc squared plus fx must all be potential energy. So
Right.
can you just rewrote that last part to be potential energy, but that still leaves.
How
gives
did
no
the half
expression.
mv squared like get turned into?
That's just reversing the approximation.
Yeah.
So
you know how we
we
did the first Taylor
Yeah.
series approximation and we got the mc squared over gamma turned into the 1/2 mv squared?
Okay.
So just do that but backwards.
Okay.
Yes.
Got it.
now
Thank you.
at this point, yes. I'm waiting for somebody to say, but wait a minute, maybe this is the one, or not.
I'm not sure.
Okay, let's
It's
go.
just that in the beginning you asked us what can you add or subtract or multiply or whatever,
Yes.
and we chose for this, but this is not the only thing, right?
No, that's a good question. Are there more ways to add some? Are there more ways than just adding an fx to make sure that our original Lagrangian that only holds for non-interacting masses becomes a Lagrangian for interacting masses?
Yeah, or even is there something else you can add on to it, which is not potential energy, or does it have to be potential energy if you add something? Or
If you're looking at mechanics, where you're just looking at things interacting mechanically, so by pushing and pulling, then it must be this particular choice. But if you also going to add, for instance, that it interacts with, say, an electromagnetic field, then this argument will not hold very well because I'm comparing it to something that does not have electromagnetic fields in it. Yes? So this comparison of this Lagrangian to that Lagrangian and therefore concluding that fx must be potential energy only holds at the moment that there's only mechanical interaction between particles. So literally, literal pushing and pulling. If not, if there was some other type of interaction, you could add this, right? I could also add an extra term that says how the mechanical particle interacts with an electromagnetic field. You get an extra term. But that term I will not get from this comparison because this never contained any electromagnetism. This would still be true, by the way. It just means you had to add yet another term. You add another one and another one for every interaction that you have. You add another term to the Lagrangian and you get whatever you want to end up with. Louis, you had a question, I think.
Oh, no, never mind.
Okay. Now, let me raise 2 points and I want to see if you have a response to it. First of all, we concluded that this must be a potential energy in the Newtonian approximation. And then I take that conclusion that holds all the way here in Newtonian approximation, I take the conclusion and place it all the way back in Lagrangian, in relativistic physics. Right? My conclusion holds in Newtonian physics, but I upgrade the conclusion as if it also holds in the non-Newtonian approximation. Is that allowed?
I don't think so.
I know, I mean, maybe there's enough freedom contained in our expression for potential energy, so we can account for it, because certainly there will be some difference.
I very much like that. I mean, I haven't specified what the potential energy is, just that there is a potential energy. So maybe there's some inherent freedom to, shift your non-Newtonianness into something more relativistic. I like that point. But there's another point you can make. So it's correct, but we can do something. We can do a little bit extra to it. We can make an additional argument. So can I conclude that this is a potential energy at Newtonian level and then upgrade that conclusion to relativistic level? That really is my question. The answer is yes, by the way. Let me help you there.
If you have an approximation, then at some point, if you do a lot of terms,
Yes.
then wouldn't you end up with a relativistic?
Well, it's certainly true that this is only the first order approximation. If V is not small and you want to make it hold for all V's, then that means your Taylor series has to have many more terms. Okay.
And they all, like this one, the first one has a unit of energy, and then the other ones need to have a unit of energy too.
I agree.
So the other terms should be energy.
I agree with you that if you would have a higher approximation, that maybe you would get more terms, and that the more terms maybe together will form the full potential energy and not just the Newtonian one. But that argument is actually wrong. Yes?
Can't you just, like we did last time, like do the dimensional analysis?
No, that's also what you're suggesting. That what you can show is that if you take more terms in this approximation, you get extra terms, and they are all energies. That is your argument. That is correct. But that's not my question.
Why is my argument wrong?
Well, your argument says if you would take V to be small but not very small, so you need not just this first order approximation but more terms, you get also more terms in this resulting expression, but they are terms that contain V's. They do not contain X's. This approximation is an approximation. Yeah, I'm sorry, I wrote X here. Maybe I shouldn't have used the letter X here. Okay, it makes you think that this is actually a position. It might. Then I think let's use the number A, but then you think no, an acceleration. Okay.
I think we get X. I think it's fine. If
yeah, but just for the people at home, I don't know if there's any people watching, but suppose that maybe we should get a different number. Can we have a
I.
An I? Okay.
Inertia.
Is that?
No, it's a small I. It can be a complex number, but it can also be a.
Maybe we should have
N.
Yeah.
N.
Do like beta or something.
No, we already have an
No, well, beta already is V over C.
This is a way.
Make it an umlaut A.
Yeah, umlaut A. I like that. There we go.
That looks like it's a
No wait, is this the second?
but now it looks
the
like
second
it's
time
the
derivative of
acceleration.
Does somebody have a letter of the non-Latin alphabet, please?
I mean, you can draw a pentagram.
Yeah, that makes it even. Oh man.
Yeah, lambda. There you go. Okay.
Wavelength?
Oh, but it's like an eigenvalue.
That's it.
Eigenvalue equation in algebra. Yes, forget about it. Okay, fine. Lambda. Now, back to her argument. Yes, you can have more terms in this approximation, but this approximation, the high order terms will only be terms in V over C, right? I mean, it's an what I'm approximating is only the V over C part. So that means adding more terms to the approximation would just add more terms that are V over C. But we were looking for something that depends on X. So the high order terms in this approximation, bringing those back in, can never contribute to X. It would just make your expression for the kinetic energy more relativistic. It will not change your potential energy.
You use
Right.
the approximation only on the first part of your.
Yes, I only use it here.
So you don't use it on the part that has an X.
Yes, but we're so close to the answer of my question now. I mean, you are so close. I don't know if this is what you were going for, but we're so close. So let me rephrase my argument one more time, and maybe we can then get everything in place. Yes. So my question was, why is it that I identify Fx as the potential energy at Newtonian level, yet I take that conclusion from Newtonian level and I use it at the relativistic level? And one argument that I've heard was, well, maybe you cannot do that, or maybe you can do that because we've made an approximation here, right, in V over C. And maybe if you add more terms to it, so you make it more and more and more relativistic, then maybe you can conclude that they should also hold at Newtonian or at relativistic level. That argument does not fly, because the best that this approximation can do is add something lambda squared, lambda cubed, something like that, right, with some numbers in front. But these are V's over C's here. So it can never, no matter how many terms I take extra in my approximation in this Taylor series, it can only add to the V over C part of my Lagrangian. It can never say anything about the potential energy because the potential energy doesn't depend on V. So whatever the answer is, it does not lie in taking more V over C terms in.
Is it just the addition of gamma? Or the
Yeah, it is
dividing
actually, yes. The only thing that I do at the moment that I take more terms in is that I approximate my gamma better and better. That's
So
really
then-
what I'm doing.
So then, if we approximate it even closer, if it's not going to change that term that we have for potential energy, if we get closer and closer to relativity,
Yes,
then this potential energy is all there must be, even in the relativistic scene.
correct. That's the right argument.
Nice.
Yes,
Doesn't that also mean that it's just the same potential energy?
it is. So that's the right argument. So for the people who have not heard it, the approximation that we made from this curly equality sign is an approximation only in the velocities. Yes? It makes no statement whatsoever about how well approximate your potential energy is. So that means the conclusion for potential energy, which doesn't even feel going from Newtonian to relativistic physics, therefore must be the same already in Newtonian physics. Or the same argument, slightly phrased differently. The fact that this guy, that we now know is potential energy, yes? The fact that this guy did not feel this approximation, it's an approximation in V, and this guy doesn't depend on V, means that this guy went through the whole Newtonian approximation unscathed. It's the same expression throughout. So that means if you conclude that it is potential energy at the Newtonian level, it must still be the potential energy at the relativistic level. Not approximately, but exactly in italics. Yes? Inside joke.
Newtonian physics is
So, we really know that even outside of our approximation, this is the potential energy. Not by approximate. No, exactly. Good. That means we are in very good position now. We have the relativistic Lagrangian that now contains potential energy. Now, what is the potential energy? Well, that depends on what system you're looking at, how you are interacting with your masses. There's one more comment I would like to make. Invariance. I've added something now that depends on x, and x is itself not invariant, is it? One inertia frame and the other inertia frame go with some gamma. See, I hear some sighing a bit. Oh, yeah, but this is relativity. Yeah, we have to keep our things invariant. The whole idea here was that the action should be an invariant number, otherwise you get different rules of physics in different systems. And one thing to make sure that that happens is to make sure that all of this is invariant. Now this is invariant, but this might not be because there's an x in there.
But is it?
So we might be breaking the invariance at the moment that we add the potential energy.
well, maybe it's in our potential energy right now, right? We didn't open it up yet. We didn't.
You're right, we did not open it up. So we still have some inherent freedom. I mean, you can have a function that depends on x, yet is when multiplied with this dt will still end up being invariant. In principle, that's not impossible. So that can be done. Now the bigger thing here is that unfortunately almost all the potential energies that we know of in nature in mechanics, right? Not potential energies due to electrodynamics, for instance, or whatever part of particle physics or whatever you're looking at, but in mechanics almost all the potential energies that we know are unfortunately inherently non-invariant. Now that has a consequence. That means that this integrated over time is invariant, This is not the new Lagrangian. Now, it doesn't mean that it's wrong. No, it doesn't mean it's wrong. It just means that the conclusion that you will get will only hold in the inertial system in which this particular V happens to hold. Yes? That's what we get. Is it our fault? No. It's just that this particular way of doing physics with potential energies, mechanical potential energies, happens to be such that the V's usually do not come in invariant terms. So there's nothing wrong. It's just something that you have to be mindful of. At the moment that you subtract an x-dependent function, then you might run the risk of getting a Lagrangian that, when integrated over time, is not invariant anymore. This part still is. This part might spoil it. And the might depends on which V over x you have taken. It's not wrong, it just means the outcomes therefore will only hold in one particular inertial system and usually not in others. Again, not wrong, just be mindful that if you put in a V of x, you might end up with a piece of physics that only holds in one or two inertial frames and not in all of them. Yeah? Good. Now, having done all this, we are now in a beautiful position because we're here. And that means we can follow any of these arrows and see what will happen with nature. So what I would like to do before the break is let's follow the first arrow. Let's see how nature will behave now that we have a Lagrangian. Right, you remember this. Once I give you a Lagrangian, you can follow these arrows. You can get to know everything that you want to know about that particular piece of nature. Let's do it right now. This one is actually, this arrow is part of the tutorial this afternoon. You can find out what the energy now is. Maybe you already have suspicion what it's going to be, but I will leave it up to you to find out. We are going to follow this arrow. We have a Lagrangian, follow this arrow. Let's see what nature does. You have a particle now. It is flying around. We are going to touch it. That's what the potential energy does. It means pushing and pulling the particle, either by electric. Well, I've decided not to touch that one at all. Okay, so what do we do? I give you a Lagrangian. I ask you to tell me how nature behaves. What is the series of steps that you take?
You need to define potential energy.
Well, but I'm going to be sneaky. I'm going to leave potential energy open. I want to have a most general expression for what nature will do. You're right. In practice, somebody has to tell you what the potential energy is. What is it that the particle is feeling? Is it a gravitational field? Is it an electromagnetic interaction of some type? What have you? Is it a spring? Is it a particle on a spring maybe? Right? And for all these things you have a different potential energy. I'm going to leave it open.
But if you're in special relativity, can you then just add gravity to it?
Yes. And that might sound, well, I'm going to block off this particular comment. So what I'm going to say now is sort of like a little bit outside of everything, but for the people who are interested, and then I'm going to do the exercise. You might, for instance, say, you know what, I'm going to look at a mass that moves relativistically in a gravitational field. Okay? Now, this is the blocked off part. Some people will say, but I thought gravitational fields came with general relativity, and this is special relativity.
But
that is correct.
But we also said at some point that doesn't matter accelerations, basically.
We discussed at some point that you are completely free in special relativity to look at particles that are moving that are moving in an accelerating fashion. Yes, even if that acceleration is due to gravity. Now, so that means, in principle, if you want to make this relativity with a little bit of gravity in it, in principle you can say, well, then I have to put in the potential energy for gravity, and maybe you know this from either your high school or from your classical physics, classical mechanics, say. Can somebody tell me what the potential energy is of a mass in a gravitational field? Or a gx?
For
okay,
G constant or not?
Gmm over r.
Yes, I mean not close to Earth, yes, because then life is simple. Because yes, close to Earth will be something like this, yeah? Something like that. Now let's shoot this mass somewhere up to the star, so you cannot take this to be constant.
Gmm over r.
Do people know this? Gmm over r, not r squared, that's the force. In fact, you can find this very easily because you know, again, that force is defined as the negative space derivative of the potential energy. So if you know that this guy is the Newtonian force for gravity, that will be something like this. But let's make it one-dimensional, so it's x here. Then you can easily find for yourself by solving this that the potential energy due to gravity, must read this with minus actually, is gmm over x, not x squared over x. So this is your basic Newtonian expression for the gravitational field. Alright, so what you could do, if you say I have a relativistic particle, that's this part, moving in a classical gravitational field, Newtonian classical gravitational field, you use this V and put in this and you're good to go. Now Alice's point here, I think, was what I thought. Special relativity did not deal with gravity. No, it does. But it deals with Newtonian gravity. Because I'm still in Minkowski space-time. So that means I'm still allowed to use special relativity. So what I'm doing is I'm using Minkowski space-time, and in that I put Newtonian gravity.
Oh my god.
All right. Now that's the
Some
simplest.
weird
Yes, it
mutant.
gets worse. Because if you want to do real general relativity, real gravitational fields, then I will show you in period 5 that Minkowski space-time doesn't work anymore. That means not only do you have to change the potential energy, you have to change the space-time itself. So that means I'm not just adding gravity due to this part by using this potential. I'm also adding gravity by having a non-Minkowski kinetic energy part to your Lagrangian. Now, what is the difference between the two? Because I have Minkowski space-time where I've added Newtonian gravity, or I just completely changed the space-time itself, non-Minkowski. The second one is correct. And this is only approximate. So can you do gravity in special relativity? Yes.
It's just another, it's an intermediate approximation step in
It is.
between
It really is. It really
general
is.
relativity and
And you might remember that at some point, I think, there was some talk of a period 3 project in physics, where I was actually going to have people use something like this, but not use this potential, but have general relativistic corrections to it. So that means you would still have Minkowski space-time, but it would pretend with every approximation more and more to be a curved space-time and see what would happen. But anyway. So that was the box part, yes? Now, as I was saying, I'm not going to specify what the potential energy is because I want to leave it as general as possible. I want to get the general rules for a relativistic mass feeling some potential energy field. Now, what do I do? How do I find how nature behaves?
well, you look
This.
at what it tells you to do.
That's
And
this thing, yes?
And that's what you do to the
Yes.
to your Lagrangian.
I take the Lagrange equation and put in the numbers. So I have to stick this guy if I want to know how nature will now behave. I'm sticking to the Euler-Lagrange equation. Now let's do both sides in sequence. Let's start with the left-hand side. So this means left-hand side, this guy. Well, that should be easy, I think. What's the answer? I take my Lagrangian, this new guy, and I take the derivative with respect to x. It should be very easy because I haven't told you what V is, so there's very little you can do, is there?
X derivative of potential.
Yeah, that's the best you can do. You don't know what V is, the potential, so well, the best you can do is it has to be its time space derivative. Now this guy doesn't feel any space derivatives because of again the curly D's. There's no x in there. There is secretly within the V, but here it's curly D's, so you have to look at the explicit x dependencies. This guy is not x dependent, so the derivative will only feel this thing. So that means it gives you minus V over x. Yes, that's the best I can do if I don't know what V is. By the way, we have a name for this in classical mechanics: the minus space derivative of the potential energy. That's the force, the Newtonian force. Good. I can sort of see Newton's second law coming out. Yes? I already have an F. Let's see what the other side is. Right hand side is this one. Goes in 2 steps. I have to take the v derivative, curly v derivative of the Lagrangian. Does this derivative, does it feel this guy?
No,
Not at all, huh?
not explicit.
So it only feels this guy. But in the tutorial last week we already showed what this is. The dl dv derivative. Or in fact, maybe this is a clue. The dl dv derivative is by definition a momentum that we derived at least in 2 ways, so you should know the answer by heart by now. What is the relativistic momentum?
Gamma and V.
Gamma and v. Now, if you don't recall this from last week when we derived dl dv, or the momentum, in the quick and dirty way, and if you don't recall this from the tutorial where we did it explicitly, it's very simple, right? Take this guy, take the dl dv, doesn't feel this part, only feels this part, you will end up with gamma and v. Well, wait a minute, that just means that this is the time derivative of the momentum. And if you recall from last week, when I don't have a subscript to p, I mean relativistic momentum, including the gamma, yes? And then Euler-Lagrange tells you, well, this should be that. So I get that in relativity, interacting relativity, force is given by the time derivative of the momentum. I would say no surprise there, because that's the same as in Newtonian physics, isn't it? The only difference being in Newtonian physics was the classical momentum. But apparently in relativistic physics, the exact same rule holds. It's just you have to replace p by the relativistic v, just squeeze an extra gamma in there. Now, to me, that's extremely satisfying. That this Lagrangian that we had, that is forced upon us by the condition that the rules of physics should be the same in all inertial systems, gives us back the natural extension to Newton's second law in relativity. We can do it slightly better. Then we'll have a break. Because, well, you can actually work this out a little bit more if you want. Because we can just take the time derivative of this thing. Now you cannot take v to be constant anymore. Because, hey, we have a space dependence to our situation, so that means the momentum cannot be conserved, so the velocity cannot be conserved. So the v is now time dependent. We don't know how exactly, but it is time dependent. And there's another v in the gamma in here, yes? So you have to go through the actual ddt of this guy. But I will give you the answer. Going through this is another exercise for the tutorial. So this tutorial exercise is just taking the derivative and being careful with your algebra. Here's the answer. Gamma to the 3 ma. That's what you get. So in other words, if you place a particle in Minkowski or a mass in Minkowski space-time, and you're completely free to make it move as fast as you can because it's relativity now, and you subject it to a potential energy, you will find that unlike Newtonian physics, where its motion is described by F is m times a, it's now gamma to the 3 ma. Yes, that's what you get if you just follow the mathematics. Here you go. This is what I would like to call the relativistic version of Newton's second law. There are people now, not in the audience I hope, but all around the world, to say, but I thought special relativity means that things only go with constant velocity, and now you say that things can accelerate. Yes, we've talked about this many times. You have to be an inertial system. But the thing you're looking at, this mass, is perfectly allowed to accelerate. How does it accelerate? Well, the force that you put on it, your basic Newtonian force, but instead of solving F equals ma, you have to solve F equals gamma to the 3 ma. And otherwise things are exactly the same. final comment. We know that if V is very small, we should get back to Newtonian physics. Does that happen? If the mass does not move too fast?
Gamma is 1 then. So
Correct. If V is very small, gamma goes to 1. Then gamma to the 3 really goes to 1. Yes. Okay. So that means if the mass does not move too fast,
Even one area.
you get back your basic Newtonian physics. That's all there is to it. Somebody gives you a force, and you know that the particle is allowed to move as, possibly at the speed of light. Solve this guy instead of that guy. Now we're going to have a break. We have, in principle, everything that we need now. If you were given a particular situation where you know what the potential energy is, you can calculate how that particle will move. I say particle as if I'm just only talking about protons and electrons. It also applies to cars and planets, right? All of this stuff. Now don't make gravity too strong, because then you are not allowed to stay within Minkowski space-time anymore. You have to go to curved space-time to describe gravity in full. This is general relativity. But aside from that, this, as long as you are looking at Newtonian forces acting on particles, masses that are then allowed to, in principle, go with high velocities. Speaking of food.
I have your waffles.
Yes! Score!
There you go.
Thank you. I paid them to bring me waffles. So, all right. So if you have a mass in whatever system, but you're not in a curved space-time due to general relativistic gravity, then you can do this. Calculate how things move. Now, from the first couple of weeks, you know how things look in different inertial systems. So in principle, we're done, and the only thing that we need to do is apply it a little bit. So I want to spend a little bit of time looking at the characteristics of this particular equation. And then let's see if we can solve it for one particular case. What is the time, actually? I hate that there's no clock here. Really
30.
Doing the math?
somebody
Half an
say
hour, okay,
gamma
good.
to-
This stuff easy. 30 minutes, hard. Let's start with some general properties of this thing, yes? One of them is that this equation has now become much more difficult mathematically to solve, unfortunately. Now, in your Newton days, when your law of motion looks something like this, then this could be a difficult exercise to solve, could be an easy exercise to solve, but it's highly dependent on whether the f happened to be a difficult f. Yes, constant f, easy. X-dependent f, probably a little bit more difficult. Very x and maybe v-dependent f, much more difficult. Not the principle, I mean the rule of physics is still the same, but mathematically going through this exercise and solving xt is something, 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 this part might actually be very difficult, yes, depending how difficult your f was. Now, a famous example of this, for instance, would be, well, let's take that example again, if this were Newtonian gravity. This equation is quite difficult to solve. You know the answers. Those are not just circular orbits, but also these Kepler orbits, right? So particles or planets moving in an elliptical orbit around the Sun. And this results ultimately in the 3 Kepler laws that you probably remember. First Kepler law says planets around the Sun move in an ellipse with the Sun in one of the focal points. Second Kepler's law is a statement about how fast it moves at any position in the orbit. The closer, the faster, according to a particular rule, a mathematical rule. And the third Kepler law says that the amount of seconds that it takes to orbit one full revolution, it's the cube of that number is proportional to, the square of that number is proportional to the cube of the highest half-axis, the biggest half-axis of the ellipse, right? Those are Kepler's third laws. This is how Newton got to his force of gravity. He got this expression because Kepler painstakingly found these 3 laws from just observation alone. The Newton said, wait a minute, if that is the case, then then the force must look something like this. Yes? So the point that I'm making here is this is difficult. It takes a genius like Newton's to just do the mathematics. A little bit of Newton pitching here. Calculus, derivatives and these sorts of things that you need to solve this equation was not invented in those days. the 1600s. So Newton, when he had Kepler's observations and had some idea of how the laws of mechanics worked, was lacking the mathematics to do the exercise. So what did Newton do? He put away his physics notebook, took out a fresh notebook, invented calculus, including multivariable calculus, then had his tools, and then got back his mechanics, his physics book, and then solved the rest. Yes, I mean, think of the genius that you must be, not only to solve the equation in the first place, no, even if you don't have the laws which they obey, Newton's second law wasn't known, the mathematics doesn't even exist, and yet you solve it all, yes? The guy did this in his mid-20s. And then he put it in a cupboard for the next 20 years, and then somebody came along, Halley of the Comet came by, and he said, "Hey Newton, I want to know how the planets work." He said, "Yeah, it's an ellipse. Solved it 20 years ago when I was 20. And Halley said, "Really? Really? How does that work?" And he said, "Well, I'll work it out for you." And that ultimately turned out, right, this big book, Principia Mathematica. Anyway, genius. Now, all of this is saying that this can be a very difficult equation depending on what the force happens to look like. Yes. Now let's go to our version. Our version looks like this. There you go. Looks like this. Now the difficulty with this equation was that you have to find x as a function of t, but at least you know what its second derivative looks like, right? That's given by this equation. Newton's second law tells you that a is equal to f over m, and depending on how f depends on x, you can integrate this 2 times over time and you get x as a function of t. In principle, you can do this. Might be difficult again, see Kepler's laws, but it can be done. Here, life is much more difficult because what you have here is that the x that you're looking for is not just hidden in here via 2 derivatives, it's also hidden in here via a square over which there is a square root of 3 over 2 power. That's ridiculously difficult, mathematically speaking. In fact, the difficulty really comes in when you consider that this is what we call a linear differential equation. And by linear, it is meant that the thing that you're looking for, the x, or its derivatives, like v and a, only appear in the equation themselves to the first power. Yes? A comes in here, a is a derivative, 2 derivatives of the x that you're looking for, but it appears only to the first power. There's no something like this or so. Or the logarithm of a. Suppose Newton's law would look like this. Yes? It just happens that it's much more simple than this. That's what we call linear differential equation. Unfortunately, this is not a linear differential equation. This part is still linear. The derivatives appear only to the first power. But the v, the first derivative, appears at the very least to the second power and then yet to another power with a 1 minus somewhere. Yes? We call this in mathematics a non-linear differential equation. And here's the bad news. There's a statement in calculus that you might have heard of before, and that says a linear differential equation has exactly as many solutions as the highest power or the highest derivative that there's in there. So this guy has at the most 2 solutions. There are 2 functions of x that will solve this. Why? Because the highest derivative happens to be a second derivative. That's it's one of the most important statements in calculus. It's a proven statement. So that means even if it is a difficult equation to solve, you know exactly how many solutions to look for. You cannot find more solutions. If I found 2 solutions, I don't have to look any further. They have to be the same solutions. There are no more than those. This guy, unfortunately, is nonlinear. And that means that rule doesn't hold. You don't know how many solutions there are. That's one thing. It gets worse. So that means if you found 2 solutions here, you don't know if you're done. There might still be another 15 around. So that's crappy. It gets worse. The worst thing here is that linear differential equations have a well-defined way of solving them. Now, we're not going to go into all the mathematics and how to solve them, but there are tested ways that always, in every situation, will give you the answer. It has to do something with Green's functions and these sorts of things. Now, if you've never heard of these things, don't worry about it. The only statement here is there is a trick that will always give you the answer. It might be difficult to apply, but it will always give you the right answer. So not only do you know how many solutions Newton's second law has in its original form, you also know how to find them, even though they might be difficult in practice. Yes?
Also, if you have like 7th order differential equation or
Do we?
something like that.
Do we?
Like
or is-
if you have.
Yes, if you have 7th order differential equations, well, then things become more difficult. 2nd order differential equations have a well-defined way of doing it.
Oh, okay.
7th order is probably more difficult.
I thought that some French guy proved that there is no standard way of solving
Non-linear or
linear.
linear? To what order?
I think it was 5th.
5th? Are you confusing this with solving the algebraic solutions to a polynomial to 5th order? Right?
Oh yeah.
It's similar, yes, but it's
Yeah.
not the same. So you're confusing two statements. Now, that means that this equation, even though it does have solutions, there's no fixed way of finding it. There's no foolproof way of finding this thing. That means every single time that you want to solve this equation, you have to start from scratch and find some ad hoc way for your particular situation, unfortunately. Cannot be made any more simple. So that sucks. Now then the third thing, it's like a doom scenario that I'm painting right now, but here's the third thing. Not only do you not know how many solutions and that there's no basic trick to do it, the ad hoc trick that you have to find per case is usually itself difficult. Okay? So, note that this has nothing to do with how difficult the force happens to be. It's not the physics, the surrounding environment that makes this difficult to solve. It's this part of the equation that has nothing to do with what force the particle is feeling. It's really inherent to nature itself, this difficulty. Now, is there anything we can do about this? No. So what people do in practice is that they solve this either numerically, that you just give it to a computer and say, well, calculate for every next microsecond where the particle should be, and then use that new position as a starting point for a new calculation, calculate the next microsecond, gives the computer a couple of seconds or a couple of minutes, and will sort of trace out the path. Yes, so you can do this in practice, but it's very hard to find analytical solutions, is what I'm saying. So that's one characteristic I wanted to point out. This is a difficult equation to solve because of the non-linearity due to the gamma to the 3. Second statement that I wanted to make about this guy, and actually due to questions that I got 2 lectures ago, I've already told you this. That this equation tells you that special relativity does not allow things to go faster than light. Right? We had a proof for this last week. We proved that the energy is equal by mc squared times gamma. And that itself shows that to make something go with with the speed of light means you need infinite energy, which is another way of saying that you cannot do it. So we know that things cannot go faster than the speed of light. But this equation also tells you so. This equation does not, because it means if you just take a constant force, right? Here, 10 Newton. Okay. Every next second you get, well, let's make it 1 kilo to make the calculation simple. That means every second your velocity has increased with 10 meters per second. So you go from 10 meters per second to 20 meters per second, 30, 40, 50, and if you keep it up long enough, there's nothing in this equation telling you that the thing will not go faster than light. This guy has inherently built in that you cannot go faster than light. I showed this to you because it came up in the discussion that we were having, but maybe you remember the argument. Why does this equation tell you you cannot go faster than light? Do you remember, or maybe you can find it out on the spot? I'm going to skip you for a moment. That's a compliment.
You need to provide like increasing force for less and less increasing velocity.
Yes, but how do you see this? You are right though, but how do you see it?
I guess, well, because A is the first derivative of velocity, so but now it'll go up more quickly than v squared to the cube.
You know, Joe, I should ask you to answer the question and at the same time eating something that's crunchy, because I sort of only heard my own crunching. Can you repeat it? I know, sorry, really, it's my fault, but can you repeat the...
Because acceleration is like the first derivative of velocity.
Yes.
So I can't see exactly mathematically, but that would go up quicker, that would go up less quickly than the velocity would go up.
So the acceleration goes up more quick than the velocity does? Because that means...
Other way around.
How about the acceleration goes down? Because acceleration going down with high velocity means that every next increase of velocity is going to take more time, right? That's what I say at the moment that I say acceleration becomes small at some point. If acceleration becomes small, then that means it's going to take a lot of time to increase the velocity even more. Now, that's sort of in there because there is a v in there and there is an a in there. So you really can see that a and v have some relationship inherently to the equation itself. So I think the only thing we have to prove is that the acceleration at some point becomes almost negligible at high velocities. So if you make v big enough, the a has become really small, which is another way of saying that it's going to be enormously difficult to add more velocity to things, yes? If a goes down, that means adding more velocity is going to take a long time. So you can see that there's something in there. Well, we can actually show it right here, right now. Because I hear the sound of understanding here. I hope so. I'm going to write down a. Yes? So let's see if that idea is correct, that maybe the acceleration at some point just goes down too much. And if a becomes very small, just repeating my argument, that if a becomes very small, then any next increase in velocity is going to take a long time. That's what you mean when you say acceleration is small. So maybe we can show that a becomes very small at high velocities. If so, then naturally it's going to be more and more difficult to accelerate things. Let's do it right here, right now. If we go back to the original form, let's use this one. What is the expression for a? Regardless of the forces, I'm just going to leave force open, could be constant, could be non-constant. But what is a?
dv over dt.
No crunching, but I didn't hear it, so.
Oh, so f over gamma cubed m?
This? Okay. What happens to gamma at the moment that you get close to the speed of light? What does gamma do?
Really
Because,
big.
here 0, I hear 1.
Infinity.
There, and over here infinity. I'm going with infinity.
Yeah.
Because our gamma, we showed what gamma was in the first lecture. This is what gamma looks like. If v gets close to c, then at some point it's going to take quite a while because it's very non-slopey at first, but at some point it will just spike up immediately close to c, and at c it will have a mathematical asymptote. Yes. So at v is equal to c, gamma becomes ridiculously big. It will go to infinity. Somebody said 0. Gammas never become 0. I mean, they start at 1 and they go to infinity and no lower numbers.
I mean 1 over gamma becomes.
So yeah, so what does 1 over gamma become at the moment that v becomes a high number?
When the acceleration becomes 0 as well. You can't accelerate anymore. So for increasing v, acceleration goes down.
Don't show this to your math teachers, but I'm pretending as if it's a number. But yes. So what do we see happening here? We see that this gamma here in the denominator tells you that if you go really fast, close to the speed of light, gamma goes to higher numbers, acceleration goes to 0. Now, that's exactly the point we were hoping to find, that apparently the faster you go, the less acceleration you will have, even though the force hasn't changed. Now, having a low acceleration means you will not increase velocity much anymore. Having a 0 acceleration means you will not increase the velocity at all. Really what I'm saying here is it's basic calculus. If you want to find the highest point in your velocity curve, you have to look for where its acceleration is 0. The highest point in any curve is when the derivative is 0. What is the highest point in v? When the acceleration is 0. So when is the acceleration 0? When v is c, because then you get gamma as infinity. So what have we found? This rule in itself, from only its right hand side, will tell you that no matter how much pulling and pushing you do, it will not go faster than light. You can get as close as you want, but you will never get there. You will certainly not cross it. That's what the mathematics tells you. Now that's a strong statement. We were teasing this for many weeks. Oh, you cannot go faster than light. Oh, we haven't proven it. Okay, we have now proven it two ways, right? From the energy last week, and we now also see it from Newton's law in relativity. Now note again, doesn't matter what your f was. You think, you know what, I'm going to increase f. I'm going to make f bigger, 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 bigger. And hopefully it will cancel. Hey, look at that.
Yes.
Who is this?
It's them. Could you reach?
Emma, was that the
Give me
question you
the
wanted
thing
to ask?
No, it wasn't.
Okay, fine. It's relativity.
I like it.
Yes, I do.
Very good.
Yes. I said I do. Me too. And you do.
Yes. Very nice.
Thank you.
You should
Welcome.
consider following the course.
I already have.
I know.
Enjoy, guys. All right.
So, there we go. You cannot go faster than light. Nature itself prohibits it. That's what we found. And yeah, the point I was making was, even if you try to compensate by making the force bigger, I'm going to pull harder at some point. Yes, okay, then still it will always lose against the gamma here, the gamma that becomes infinity here. Maybe in some very strange situation where you say I'm going to make the force infinite, maybe you can sort of cancel it out, but I think having an infinite force is...
Or the mass zero.
Or, yeah, well, there's the mass zero thing, because you get infinity times zero. Yes. And infinity times zero is undefined, which means this might not be zero anymore. Okay? But then again, having a mass of zero is the same thing as saying you're not allowed to use Newton's laws in the first place, because mass of zero requires a different Lagrangian than either this one or that one. So that means you, for masses of zero, where we saw last week things have to go with the speed of light, you have to start with a different Lagrangians to begin with. So, that's all pretty cool.
Can you investigate what would be 0 times infinity?
It's highly context dependent.
But you can do it.
Sure, yeah. I feel this is what you're going to do tonight, yes? Okay. Okay.
But
yes. No, please.
No, it's too late now, you got to say it.
can't you say the same thing, which is, if you say that if v goes to the speed of light, you would have to have an infinite force to maintain a constant acceleration?
That's, I think, the same thing as saying that you maybe can compensate this infinity by introducing another infinity in
Okay.
yes.
Yeah.
No,
okay.
I think that's true.
Well, I just,
No, I think that's I think that works. But I think we're
but that's the same as saying that you can't accelerate. That we're going to the speed of light, your acceleration will go to zero for a constant force.
well. But I think at the moment that you have to apply something that is infinite in nature, is another way of saying that it cannot be done, right? I mean, on paper you can talk about an infinite force, but if you actually have to apply it in practice, you can make big forces, you cannot make infinite forces. So the cancellation, hopefully, of this gamma with this infinity over here, with this f, by making f infinity, that can be done on paper. But applying an infinite force is another way of saying that it cannot be done. So now, I'm going to take a couple of minutes to hopefully dispel an argument that sometimes you see in the books, which is wrong. I've mentioned this also a couple of times, but now is a good time to wrap everything together. In the books, you tend to find that the reason that you cannot go faster than light is because mass becomes bigger. Unfortunately, this statement is ubiquitous in, it's going to sound very elitist, but in non-expert books on relativity. I don't mean it elitist, I mean this is a statistical fact. If you take a book on relativity where people don't go too deep, then this is usually what they say, why you cannot go faster than light. They say, well, the mass increases. The faster something goes, the more kilos it will have, and because of the more kilos, that means it's going to require more pushing to push it even faster. And at some point, the pushing that you need is going to be infinite. That is the argument that you hear. This is wrong. It's not just wrong in the sense that I would phrase it differently, it's fundamentally wrong. And it gives you, well, let me give, just wondering if I should first show you the general statement or should give you a thought experiment. I'm going to go with the thought experiment, yes? Okay. Now, I think I might have mentioned this particular one to some individuals every now and then during the course of this course. But I think it's nice to share this one with everybody. Suppose that it is true that mass actually is dependent on how fast the mass is going with respect to you. Yes? Now, if you're going to see what my weight is, I happen to know because I weighed myself this weekend, not for this purpose, but I do know the number. It's 87 kilos, okay? So I'm 87 kilos and I'm standing on scale right now. And the display actually says 87 kilos. And you stand next to me and you look at the display and say, oh, look, 87 kilos, good for you, or bad for you, or whatever. But you will say 87 kilos. Okay, but now that same person will start walking past me, looking at my display. And walking very fast, fast enough to make maybe, according to this faulty logic, that the mass will increase. If that person will run with respect to me and while running look at my scale, will that number be 87 or will it be different?
Well, according to this logic, it would be different.
It will be different, but does the scale know about another person running past it? How would the scale possibly know that one of the people looking at it is running? Oh, wait, I see you run, I'm going to change my number now. No, it's ridiculous, it really is. Okay? So that's simply wrong. And to make this argument a little bit more, maybe spectacular, is one that I came up with a couple of years ago. I think captures the flaw in this logic, that I would like to take a mass dangling from the ceiling, and underneath I put a little button.
Destroys the world.
And it destroys the world, obviously, right? Earth will explode, or what have you, or the train will explode, or Jaco gets a book against his head, something like that. But something will happen, yes? Now, then I take that the tension in the string, the max tension it can have is, well, give me a number, I'm going to make it 100 newtons. 100 newtons. If you try to dangle more on this string than 100 newtons, it will break. The material cannot withstand more than 100 newtons. Okay. Now, that's not too bad because it so happens that the mass is only 10 kilograms. So it means close to Earth. It's about 98 newtons, yes? So that means the string will not break. Fine, that's good because then that means the world will not explode. Now you start running and you run past that thing. Then this logic will have you believe, oh, but wait a minute, then for some reason the mass knows that you're running and will increase its number. And hey, if the number increases, you will go past the 100 Newton, depending on how fast you run. The string will not hold it anymore, the thing drops down, Earth explodes. So all of a sudden...
Isn't that compensated by a relativistic Newton signal? The force, the tension force?
I will get there in a second. Let me get there in a moment. Yes.
No.
Just to first show you that there's a paradox here. Because that means, depending on whether you are running or not compared to this dangling mass, the Earth will explode or it will not. Now, you're used to paradoxes in special relativity, yes? Sometimes somebody's number is not somebody else's number, but those paradoxes say that only numbers might be different, but the actual physical outcome is always the same. This is a real contradiction. A paradox is sort of, it looks like a contradiction, but if you look more carefully, you find everything is fine. This is a real contradiction. The Earth explodes or it does not. In fact, if I stand next to this dangling thing with the button on the front, then to me, the Earth will not explode, and then the other guy will start running, and then for him, the Earth does explode. Now, how can the Earth explode? Well, I'm still standing on it and not see it explode. This is really a contradiction. It really is simply not true that mass increases. Now, you might say at this point, yeah, but wait a minute. Maybe due to the running, this number might change using this logic, but maybe something about the string tension will also change. Yes? And maybe the max string tension will also increase in a certain amount, so that means it will still not explode or something like that. That could be, because, values change between inertial systems. So maybe the act of running might change this number in your frame, but might also change that number, and therefore it will still not break and the Earth will still not explode. But that will not work. Because the best that relativity can do, in case of vectors, and remember, this is a vector, it has a direction being straight down. Relativity can only change things along the direction of motion, right? Lorentz contraction only happens in the direction of which you are running. Now, by design in my experiment, I make this 90 degrees, so me running in this direction will change this number, will not change anything about this vector. The only thing it might change is the string tangents in that direction, but they do not matter for my experiment. There's no way that you can weasel ourselves out of here by saying something, well, maybe something in the string will also change. It simply does not work. Yes?
Isn't there a mistake in the entire logic, and that is that even though we're dealing with special relativity, you still assume that the equivalence principle holds, which doesn't have to hold. And then Newton's laws applies to inertial mass, whereas what you're using there is gravitational mass, and they wouldn't be the same thing, so the inertial mass could still be changed.
I fully understand, and there's a subtlety there, but the only thing it will change is how fast it will fall. Right? Because
But if the gravitational mass wouldn't change, but the inertial mass along the traveling
so which
thing
one would change, according to you?
The inertial mass would change, the gravitational mass wouldn't.
Okay.
Therefore the string wouldn't break because the gravitational mass didn't change.
That's a very good argument.
And all your forces still work out because the inertial mass did change.
That's a very good argument. And there might be people not following this because he's relaying on something that comes from general relativity, and he did the course already last year. So let me be brief in the answer. We can discuss this in person if you want, but that means that the equivalence principle is broken in one inertial frame to the next, which means general relativity can by definition not hold in all inertial frames anymore.
Oh yeah, that I completely agree with.
Yes, so that means that if you're going to assume that inertial mass, gravitational mass, that one of them changes but not the other one, then it means you're excluding general relativity to be true in all inertial frames.
Oh yeah, no, I'm just saying for special relativity it could still work perfectly fine.
Agreed, but if you want to generalize it to general
Yeah, no.
relativity, then the argument does not hold. If you're not following this, don't worry.
No, that I agree, okay, no,
Okay,
that's
good.
perfect.
But no, but it's a very good argument, and I thought about this myself to see if my example would still hold, even in general relativity, or even because of general relativity, it should still hold. Anyway, back to the main point here. Introducing the concept that masses really increase due to your relative motion comes with real contradictions. So that means that argument is simply wrong. I'm going to make the same point, but now in a more mathematical way. Suppose that you would say, we're going to follow this logic a little bit more, that you say, well, if you start moving, you go to a different inertial system, that's what this arrow means, then m becomes a bigger number. The way that people get to this realization, again it's flawed, but to this realization is because of this equation, right? This equation is true. We proved this in many ways now. But these two guys together, some people call the relativistic mass. Gamma times m, they call the relativistic mass or so. And the relativistic mass, by its definition, does increase with high velocities because gamma increases. This m, we would call that the rest mass, m0 or so. That one stays the same. But if you include the gamma and you call this new thing gamma times m0, you call that thing the relativistic mass, then yes, indeed, it's true. This guy gets bigger if you increase your velocity with respect to it, yes? So that argument is completely true. But this might give you the wrong impression that the only thing you have to do to change Newtonian physics to relativistic physics is just take mass. Everywhere that Newtonian physics says there should be a mass, you replace it by relativistic mass. Right? You might be tempted to do that. In fact, it works here too.
F equal ma is not the same anymore.
No, but here you can see it, yes?
Yeah.
But this argument sort of works. The idea, well, maybe you can just take Newtonian physics and wherever there it says mass, you replace by gamma times m, and now you have relativistic Newtonian mechanics. And in some places that works. The momentum here, I don't know where it is. The classical momentum, as you know, is m times v. And then you could say, oh, but wait a minute. If I replace m by the relativistic m, then my relativistic version should be this, which is true. This might tempt you to think the only thing you have to do is replace Newtonian m's by gamma times m, and then everything from Newtonian physics becomes relativistic. That works here, and it works here, but that's the only two places where it does work. Because if this is Newton's second law, and you apply it here, you would have gotten 1 gamma. It's not, it's 3 gammas. We derived that. So that's my second reason why you should not be tempted to get into the habit of replacing masses by some mass that increases with velocity. In some cases that works, for instance here, but in many cases it does not. Now why it does turn up in books, that really angers me and I think should be banned as quickly, should be burned with fire, those books. Okay? So, final point, and then I think we should stop because then I've made all my points for today. The final point that I would like to make is this. Ultimately, special relativity is a theory of space and time, right? Our starting point throughout everything was just a relationship between space and time, namely the invariant line element, Minkowski line element. C squared dt squared minus dx squared is invariant. That's all that we've used throughout the whole derivation of everything. Everything on this board and the boards from the second lecture onward was just that statement and that statement alone. I promised you this when we started in the second lecture. I said this statement will derive all of special relativity that we have. Now that means that special relativity again is a relationship between space and time. So is there somebody who can maybe turn the impossibility of making things go with the speed of light into a space-time statement? I have it here as a statement in forces. Last week we had it as a statement in energies. But ultimately, since special relativity is a theory of space and time, we should be able to boil it down to a statement about space and time. Is there somebody who can make a statement? Why can you not go faster than the speed of light? Simply based on a space and time argument. No forces, no energies, just space and time. Should be possible, but can you see what it is?
From this equation?
No, not from this equation. Right, I mean, we have seen it from this equation. We've also seen it from the energy equation last week, gamma mc squared.
Well, because any time interval will become infinitely large.
Okay, yeah, no, that's correct, yes.
Distance will become infinitely small for a person going at the speed of light.
Okay.
Theoretically going at the speed of light.
So I hear a little bit of Lorentz contraction in your argument and a little bit of time dilation. Yes?
Yeah, so Lorentz transform.
Okay, that's good, because a Lorentz transform and its derivatives, namely time dilation and Lorentz contraction, are indeed statements of space and time. Suppose that I want to push this chair, yes? And I'm pushing against this chair. And suppose that it has an acceleration in this frame, that it gets, just making up a number, it gets 10 meter per second extra velocity for every second that I push. Yes? The acceleration therefore is 10 meter per second squared. Okay. I'm pushing it against that thing. That means in this frame it will take 1 second for us to see me accelerate that thing with 10 extra meters per second velocity. Now, you see me push against this chair while you're moving with respect to me. What will happen to the amount of time that you see me take me push against the chair? I have a process. The process being I'm making the chair go faster with 10 meters per second. So there's a delta t involved. In this frame, that delta t is 1 second. Is it a bigger or a smaller number in your frame if you see it from a velocity?
Faster?
I'm asking bigger or smaller. So
Oh, sorry.
Smaller number, right?
Smaller, right?
Wouldn't it be, if I say, I don't know, but if it's faster, then wouldn't it be a larger number because it's being multiplied by c? So if it's a larger fraction, then it's closer to c?
well, I'm really asking about time dilation.
I mean, you
If
just
you see some process happen and it takes delta t in one frame,
Mm-hmm.
and you look at that process from a different frame, does it take more or less seconds to see the same thing happening? It's time dilation that I'm asking now. Do things go so in slow motion if you see them happen from a velocity, or do things go faster if you see them happen? Slow motion. So it is going to take more seconds for you to see the process occur, yes? If the process is me getting this chair to a higher velocity, getting an extra 10 meter per second velocity extra to it, and to me it takes 1 second, then you seeing me push a thing 10 meter per second fast is going to take more seconds. Agreed? So that means the acceleration in your frame, that the acceleration that you see me exert on this force is going to be a smaller number than in my frame. Yes? Now that acceleration goes with a gamma. That gamma goes to infinity. So at some point, if the chair is already moving with the speed of light, that means in your frame, the next 10 meter per second that I want to add to its velocity is going to take an infinite amount of time. That means you will never see me push a thing faster than the speed of light. So that's the third reason why things do not go faster than light. One of them was the energy of last week. This is another one, and ultimately it's all just time dilation. It's going to take an infinite amount of time for you guys to see me push a thing faster than the speed of light, because time dilation is stretching the amount of time to infinite. It's just a time dilation effect. It has nothing to do with masses. It's time dilation that does it. Speaking of time.
It's 7 minutes over time.
Oh, we're over? Okay, we'll go to the different inertia frame where the 7 minutes are given back to you. In the tutorial, we're going to solve this equation for a particular case.
I just imagine always 2 jars and they're filled. One's time, one is space.
Yeah.
So a person traveling relative to you, they can have more in space. And if they're more at rest relative to you, they have more in time.
I thought you were going to say like pouring water into it, that would be time dilution. But that's
Time dilution. Actually, I was making a similar couple of years ago.